All right, what's up, everyone? We're here with week 60 of Chill Kernel Hacking for Fun. Welcome. As usual, let me do my tests of the chat and everything. Today we are working on the network driver again. It's our third week or so now of doing this. And we'll be doing some debugging today because it did not work last time. All right. Oh shit, I think I forgot to actually add the link in my tweet. Delete. All right, let's try tweeting that one more time. Yeah, hope everyone's having a good week. Whoa, frame buffer, what's up? Ooh, first one, also Kidar Codes, let's go. Good to see you guys. Hope you're having a great one. Yes. Yeah, what's up guys? How's your week? What'd you get up to? Work on any cool projects or anything like that? All right, looks like we are live indeed. So I'm just gonna close my million browser tabs, get the OS dev one up here. Wait, no, I have a bit of prep work to do. I need to get my documentation out as usual. Yeah. Give me 1 second. E1000 manual. So just me? I'm good, thank you. It's the beast I've been working on for the last month. Nice. Okay. Got Twitch going. Got YouTube going. Got the chat widget going. I think we're looking pretty good to get going today. I was watching a stream, it was like you're watching it just to listen to his voice, huh? It's funny. It's not the glamorous scraper process of rebuilding information models. Nice. All right. Well, I'm excited to get into this. Testing out the soundboard.
This is a certified hood classic.
So we are here again, back for another session of network driver development. And this is going to be kind of a challenging stream because it didn't work last time. And I kind of ran out of ways to debug it. Yeah. Okay. So yeah, here's what it kind of, let me get back into my kernel dev state. So where's the code? Here's the code. So we were working on this driver, and it's not really a very good driver. It's kind of just very quickly sketched out. But roughly what it does is it has this function that is kind of like a callback. And so when the PCI scanning code finds the driver, it calls this function. Function does two things. It initializes the NIC with this function, E1000 init. And then we just try to transmit literally a random buffer of data. It doesn't actually matter what's inside this. In fact, right now, it's an uninitialized buffer. And the idea is that if that is all working, we should see a pcap file, actually. Wow. Here. If that all ran successfully, we should see a pcap file generated at the end with the data that was transmitted. The problem is that we're not seeing that. So it will be time to debug that. And we're just, I don't know how to do, like, I am literally on the spot going to try to do this live. I think I commented some stuff out that was maybe important. What's up, useless? It's not going well. It doesn't work. But we're gonna figure out why. At least we're gonna really try to figure out why it's not working. So I have this kind of basic version staged. This can go. Sub Afnan, thank you for the test 1. So, right, we're seeing a couple things here. Most importantly, we're seeing our index 0, road to 10K, what? Yeah, it's wild. I don't know what's going on, but somehow I have 7,000 subscribers on YouTube, which is mind-boggling to me. Yeah, so big thank you to everyone that's watching. Okay. What's up, Digitalized? Nice to see you, dude. Hope you're all doing well. Yeah, feel free to post what you've been up to this week. If you've been like working on any cool projects or just like went to work or something. I don't know. I had a pretty good week working. Yeah, just chilling this weekend. Right. So briefly, E1000 init. We set up a few registers to point to important things. So we set up a pointer to the ring buffer, which is this array of descriptors. We initialize the length of it. We set the head and tail pointers to 0. And we set some various control bits, notably the enable bit, and some other stuff which I actually think is not used by qemu. And then we read the status register. Nice. Oh, Digitalized, you did the page table lab. Oh, nice. I wonder how different it was from the one that I did, but that's cool that you did it. Knack, recommend getting into drivers and kernel dev. Honestly, I'm not like an expert, so what I've been doing has been working great for me. Also, Digitalized has been doing this also. We're just following this free MIT coursework that's online. Digitalized is doing a bit of a newer version of the class than I am. He's doing they're doing the RISC-V one. I'm just doing the x86 one. I would say the difficulty level is moderate. You need to have some experience before doing this. And if you don't have experience yet, you should just do pwn.college. I'll just link to it below. That's kind of my general recommendation, is if you're kind of a beginner, first go to pwn.college and learn about C and systems. And then when you're ready, you can move on to OS development. Right, so that was initializing the NIC. Step 2 is doing a transmit on the NIC. And that's So that function receives the driver and a buffer. We check if the length of the given buffer exceeds this thing I'm calling the backing buffer. So every descriptor in this ring buffer has a backing buffer, basically. I guess I don't know if I have a visual anywhere. But we basically have this ring buffer of these descriptor structures, and each of these points to an actual buffer where the data is stored, which I'm calling the backing buffer. And for the moment, it's a limited size. It's these, I basically just allocate a page of memory and divide it evenly between 32 descriptors. And that's just the fixed size per descriptor transmission for the moment. So just check if the buffer is greater than that, then I return an error. And I'm also kind of doing this wrong, but I'm just basically grabbing the head and tail of the ring buffer and checking if the tail is currently pointing at the one behind the head, which means the buffer is full. 2021, you had to get a copy of the kernel page table for every user. Address space was the main one. Yeah, I think I remember that part. I actually specifically remember a bug, like debugging this, I think, in one of my streams, where I wasn't actually copying the full page table correctly or something like that. Okay, that's all details. None of that really matters right now because all we're trying to do is do literally any kind of transmission at all of any data at all. So this like fullness size, this like fullness check doesn't really matter because we're just sending one descriptor. And so the buffer is going to be empty. So what we do is we use the tail pointer to actually get a pointer to the descriptor, which is that structure that's here in the ring buffer. We call this function, which is like badly named and inconsistent. We formatted with the rest of this code, and we use it to actually get a pointer to this descriptor's backing buffer, which is very simple. All we do is we just compute an index into the global buffer, and just multiply by the index and the buffer size. So that gets us the pointer to this descriptor's backing buffer. Then we simply do a mem copy of the given buffer into the backing buffer, which is safe to do because we've already bounds checked the length and guaranteed that it is at most equal to the buffer size. Then we initialize the descriptor, and I zero it out completely, and I set what I believe to be the most important bits in the descriptor. The descriptor has all sorts of entries and I guess members in it, but the most important ones are the pointer to the backing buffer, which is this p buffer thing. Also the length of the data inside the backing buffer. And lastly, a command. I believe those are actually the most important ones. We can check the manual for that. Couple key things to remember are that this pointer to the backing buffer is a physical address, which is why I'm using the paddr macro. Otherwise, we'll get kernel virtual addresses. Number 2 is pretty simple. The length is just the length that we were given in this function. And then lastly, the command. And we can find out what commands are available somewhere. You know, I really thought I copied and pasted more stuff here, but we can find out what commands are available by going to the manual and looking at the legacy descriptor format, which is the documentation that describes the descriptor. I'm just gonna copy this in there because it'll be useful. So I will add today's date. It's the 23rd. And we're at episode 60, or stream 60. And so buffer address, length, command, and here is the command. So I'm even going to highlight this because it's important. Yeah. All right, checking the chat. I'm frame buffered, so sort of tempted to do this one, but go blind and learn Rust following along. Hey, do it. If you're up for a challenge, I'm not gonna stop you. There's like, wait, if I'm gonna refresh on assembly notes for the trap lab, hardest part, page was just understanding the level 3 structure of it. Oh, are you doing 64-bit then? If it's 3 levels. Okay, is the command correct? Looks like you had hex 90 previously. Let's check that. I'm not actually totally sure. It might be possible I have a bug there. So my goal was to populate the command buffer with a few things. I wanted to populate the RS bit. So this is important because this is how the NIC notifies us when a packet gets sent. In the command field, we say yes. We want the status to be reported, and then when the packet gets sent, the NIC writes the DD bit in the status part, in the status field. So we want bit 3, and we want bit 0, I think. This is where I'm like a little bit less sure. All right, we want a couple of things. I think the rest is pretty much optional. And so that was kind of the goal with this line. So the goal here was to enable bits 0 and 3. And maybe I did that wrong as the command. It looks like you had hex 90 previously. And this thing is hex 9. Oh, you mean based on the comment? I see. I think yeah, ignore. I'm not sure. Yeah, I'll explain that in one moment. Yeah, I think this is actually more correct. Also, John, what's up, dude? Hope you're having a nice day and the OS hacking is going well on your side. So, right, yeah, so I had this comment here as kind of a debugging thing, but if we ignore the comment for now, I believe this is correct because based off of the manual, I'm trying to enable bits 3 and 0. in this 8-bit register. So the reason I had hex 90 here, or okay, I will explain that in 1 minute. I'll get back to that. So then basically what I was doing, I have like a hex dump of the descriptor just to see it, basically. And then lastly, I'm updating the tail pointer in the ring buffer. And this wrap index doesn't really matter because we're just doing literally a single descriptor, right? But we are writing back to the tail register just literally the same value, but incremented. Mario, what is up, my guy? Nice to see you. Let me get my, where's my mouse pad? Shit. Let me get my mouse pad. Official Mario mouse pad. Appreciate that. Hope you're having a nice Sunday, Mario. Doing whatever you're up to, whether it's writing or whatnot. All right. So yeah, and that's it. And presumably that actually should be all that's necessary to submit a buffer to the NIC to transmit onto the network or whatever. So let's run it. So I'm just going to compile it. I think nothing really changed. So when we run this, here's what we see. This is all the normal boot boot messages. We see this normal line. It's normal to see the TX disabled thing. I think they explain that a little bit higher. Yeah, it says, so back in exercise 5, it says you should see a TX disabled message since we write to the tail register before the NIC is enabled. So that's just, that's talking about right here. Whenever we write to the tail register, qemu prints out a debug message, it seems. But at this point in the code, the NIC isn't initialized yet, or rather, the transmission functionality is not initialized yet. That happens like 1 line later when we initialize this. So therefore, qemu prints out transmit disabled. So that's expected. We have this printout saying status with the status field of the NIC, and that's also as expected. And then we get into the new stuff. So then we get into the transmit code, and here's what we see. We see the hex dump of the descriptor, and then we see this E1000 index 0 line, which is actually from when we updated the tail register, and it tried to do a transmission, basically. So that's the current state of affairs. And if this was all working correctly, we should see a PCAP file generated by qemu. And we actually do. And the problem is that it's empty, I think. I've tried opening it with TCP dump and also Wireshark, and this thing is empty. It says no packets in Wireshark, and also TCP dump doesn't say anything. So that's the problem, and that's what we're trying to figure out today. Why is that PCAP file empty? I'm just going to pose the question and talk to myself. Why is the PCAP empty? It could be for a few reasons. The most obvious reason, the code is broken somehow. Even though I think I'm doing everything correctly, I'm not, and there's some missing configuration or something like that. Another reason might be though that my system is just misconfigured or something like that, and like maybe my I don't know, my qemu flags are wrong or something weird like that. I don't think that's the case. So just to prove it, I'm going to delete the pcap so we don't see that anymore. And then I run it and it's back and there's nothing in it. John says, I would verify the bug isn't in qemu, maybe add some printf statements around the code path that leads to adding the packets to the pcap. Yeah, that's a good idea actually. And we can do this. So here is, where is it? Yeah, that's actually a really good idea. If I can somehow find my qemu window. So that's one approach we could try. If you never see them, and your driver is definitely busted, but if you do see them, then something even weirder is going on. Yeah, so the suggestion is to find the code in qemu that writes the pcap file and then add a bunch of prints to yeah, like see if that's happening or if that's not happening. If you never see them, the driver's busted, but if you do see them, something weird is even going on. Yeah, I was slightly trying to avoid doing this because I don't really want to dig through qemu too much to find that spot in the code, but maybe it's also not that hard. So that's a good idea. I'm just gonna note that down as a debugging strategy. We could add prints to qemu at the code which adds stuff to the adds data to the pcap. If we see those, if we don't see those prints hit, the driver is busted. Otherwise, the driver is working, but the file is weirdly empty for other reasons, which is probably very unlikely. Yeah, my other idea is I actually have a version of XV6 from 2022 open right here. And this, I don't know, this also has a driver. It's not complete also because it's from the coursework, but it actually has a lot of the initialization code that pre-existing, and it's kind of different from mine actually. And another way I could proceed is just to actually like copy a bit more of this code into my driver and see if that fixes anything. I can probably ignore a lot of this. It does the receive initialization also, but I am not doing that right now. It has some stuff about interrupts. It has some stuff for receiving, which I again don't care about. It does the same initialization that I do, although a little bit differently without the structure. It's actually not that different. And it asks for receive interrupts. It's actually not the difference. The main difference is that it initializes the ring buffer in a kind of specific way. Okay, I'm just going to copy and paste this also. It initializes the buffer in kind of a specific way, and it actually goes out of its way to set the DD bit on all of the entries. When it initializes the ring buffer. I am not doing that at the moment. I'm actually a little bit unsure what the state of the buffer is in when I think it was 0, but actually maybe it's completely not. I actually, yeah, forget. When you have a global C buffer like this, is it 0 initialized by default or not? In C, global variables with static storage duration are guaranteed to be 0 initialized if they don't have an explicit initializer. This means that your array of structures will be initialized to all zeros by default. Okay, so I will trust that it's all 0 initialized. But here it is actually setting the status bit on each of them. And that actually is so I think that's actually related to the transmit handling. So in my version of the code right now, I have this like comment about this kind of like race condition because I'm apparently doing the fullness check wrong. And I think the correct way to do this is actually to check these DD bits if they are set, and if the DD bit is set, then that means it's available to be written to. I'm just going to quickly try that actually and just see if that happens to change anything. I have a slight suspicion that it might. Where should I do that? I don't really know. 0 I less than k num plus plus. So, yeah, okay. So G TX descriptors I dot command equals, it's not 0, it's DD. How do they do it? And they just have, have this constant here, which is actually just a 1. So for the moment, I'll just set DD. And I'm just going to actually do a hex dump just because I'm curious of this. And I'm going to dump size of GTX descriptors. This might be kind of large. I don't actually know what I'm expecting to see here, but just out of curiosity, that would be my first guess. Ooh. Hex dump is not defined yet. It's way lower. Okay, that did not work. The file is still empty. But now we can see this nice dump of all the descriptors, and we can check if it looks like it should. So the descriptors, I always find this so confusing to read. So, we have 8 bytes of address followed by like 4 bytes of this part, and then we're interested in the command bit. This is 1, 2, 3, 4, right? So 8, then 1, 2, 3, 4. So this looks right to me. Yeah, because you go start from right to left and then top to bottom. So on the 4th byte of the 2nd row, they could have at least aligned the diagram. Yeah, that is so true. That is so, like, the widths are like super off. Yeah. Okay, so I'm pretty confident that's correct, which is kind of unfortunate because that did not change anything, so I'm just going to record that. Initialize the descriptor ring with DD. Didn't work. That was the main idea. Actually, one very weird thing that they're doing in this like MIT reference thing is they are not like using the physical address of the ring buffer as far as I can see. And I am going out of my way to do this with the p-adder thing. And I'm pretty sure that was also in the documentation elsewhere. The pointers to these arrays, as well as the addresses of packet buffers in the descriptors, must be physical addresses because hardware performs DMA directly to and from physical RAM. So I'm kind of suspicious why they are not doing this, which is maybe a reason to not trust this code. I kind of did not want to go through the effort to like get it building and like compiling and stuff. So I didn't actually run it, but that's weird. 2022, yes, I think everything after 2018 uses RISC-V. If I just search for RISC-V, yeah, there's a bunch of RISC-V stuff. Yes. Okay. Yeah, maybe we'll quickly try John's idea. So where would I find? I'm just like grepping for the word pcap. Dump. Actually, just to start all the way at the beginning, let's look at the make file. So here's where this all begins. We pass a flag to qemu. Specifying some stuff. I have double checked this. At least I asked AI if this looked right and it said yes. It's possible this line is wrong somehow. And that is the reason. I kind of don't think so, because it's not that complicated. Filter dump ID dump 0 net dev. There's like only one net device. So it seems fairly legit. But anyway, that's where this whole thing begins. Okay, which is not actually that helpful. There's not a lot to directly grep for. Either way, would you think you'd need the physical address to address the network device? I would definitely think that whatever addresses we give to the NIC from memory should be physical addresses. That would make sense to me. Oh, actually, wait. So before we go super deep, we missed kind of one thing to explain, which is this part, actually. Are you already invoking with trace? Even without the E? No, I don't think so. Thank you. Trace E1000 E. Cool. Let's try it. So did it work? You'll need to escape that. Here's what I have so far. I don't think there was new logging, unfortunately. So, yeah. Yeah, yeah, I don't know. Okay, so back to qemu. So, grepping for the word pcap. I think it was more, yeah, it's almost certainly here. This is like the dumping code. It's like the dumping code of qemu. So it might actually be kind of easy to do some prints. Dump cleanup, dump receive IOV. pcap file header. Where is this used? Dumps init. Okay, here it is. So this is actually not that hard to read. This is a function that takes a file name to write to. And actually, okay, this writes the header. And I think that's what we might be seeing. I think we're just simply seeing it write a pcap header. How big is a pcap header? -d. All right, thanks. Thanks. Let's try this. D space trace. Okay, cool. So far, I did not see anything new. Just curious, qemu, CLI args. Tracing. What is this all about? Qemu log file, actually no. But it's empty. one more time, just to be sure. The qemu log is empty, but where does that come from? Do I also specify this? Or does qemu automatically generate a file called qemu log if I delete it? And then run this again. It appeared. Okay, so it seems like qemu generates this empty log file every time. D space trace colon E1000E asterisk, right? So this is what? 4, 8, 16. 24, which is actually the size of the PCAP. So I think it's just writing the file header, and that's it. But I'm interested if, not sure why that was work. I have something. Crazy. I'm not sure. Qemu trace help to print a trace points. This option is only available if qemu has been compiled with the simple log or ftrace tracing backend. Wow. Was it trace help? So there's definitely a bunch of trace points for the E1000 thing. But it might be possible that these are not, like, the E1000E might actually be a different network card. Yeah, I'm not using Brew because it didn't enable the logging for the NIC. So, right, so I think, yeah, a lot of these might not be for the NIC that I am using. I think, so I don't really understand much of this code, but we're in E1000.c, and it has a single trace point of this receiver overrun, but I don't think it has anything else. Core, right? However, these other, yeah, I don't know. The other NIC seems to have some more of that. Bummer. Okay, that would have been cool. Right. I think the idea to look at qemu was still good though, and maybe add some prints. So I think file name would be kind of interesting to search for, because maybe there's another part of the code no. So pretty confident that this is being called because it writes a header which is 24 bytes. Actually, we can even probably just so what is the pcat magic? A1, B2, C3, D4. Yeah, it looks like it. Dump, receive, IOVAC. SFD. Wait, what happens to this FD? It gets stored in S, right? So if we look for close, yeah. So it would have to be here. This is where more data gets written to the file. So I'm going to trust qemu folder. So can I just ask, I add a basic print statement here. Well, that's kind of stupid. I didn't know if there was a special qemu specific way or something, but let me go in, and then now I can build the new qemu. Actually, I'm just going to add another one just to make sure the print is working, because that's probably not going to fire. Yeah, I'm just gonna say hello net dump state init. So now if we run this, hello net dump state init. So that means our qemu print is actually working. But as we kind of expected, this function is never getting called for some reason. The interesting thing, okay, back to this line though, it might be worth taking a closer look at this line. Yeah, because what is kind of interesting is that the MIT course lab gives us a reference of what it could look like. And I think we're close, but not exactly it. So maybe it would be good to also find the part of qemu that prints this. Probably going to be here in index here. So here we are in the start transmit function. Here's that thing where it checks if the NIC is enabled and then prints disabled. Otherwise it like does some stuff. And then here's the part where while the buffer is not empty, like do some stuff. And so we can see that it's printing out a couple of things. It prints out it prints out the value of the head pointer. It prints out the buffer pointer that was in the descriptor. Then it prints out two things. It prints out the lower word of the descriptor and the upper word of the descriptor. And I will just come back to my code so we can really closely correlate everything. So anyway, basically what we're seeing is index 0, right? It's processing the first descriptor, which is at index 0 in the buffer. The next thing is this address. Which is that buffer address, which for me is this thing right here. So for fun, we could just go and print out, yeah, we could just do a debug print. And we should expect to see the same thing. So this thing is this 4415E0 thing, which is exactly what we see in the print line. So that makes sense. But then the more interesting part is this next thing. Which is the lower word of this. So the lower word is command, CSO, and length. I think that's what we should be seeing here. So here my is this still visible? Yeah, my backing buffer size per descriptor is 128. Okay, that's weird. Which is hex 80. So that makes sense to me. And that is it's a 16-bit length. So that's up to here. And then we have the CSO, which is like, I don't know, some other thing, which is 8 bits. So that is the next thing, which leaves us at our 9 for the command register. And to me, that looks right. Because if we go back to the command register print, which is here, we wanted to activate bits 0 and 3, the RS and end of packet bits. And that's going to be 9 if we did that. And then we're not we're not seeing the extra 0 here, basically. The very strange and interesting thing is that theirs looks different, right? Because they have some different buffer size. So that's the bottom 4 nibbles. Then we have 1 byte for the CSO, but strangely, they have a 9T here instead of just a regular 9. And that's kind of interesting to me, because to me it looks wrong. Like, that would mean so that the hex 2A is their length, the 00 is their CSO, and then 9T would be their transmit command, right? Which would mean they are setting like bits 7 and 4, which sounds totally wrong to me. So that is very interesting why they gave that to us as the reference. They said you should see something like this. I don't know. So either that's wrong and kind of misleading, or actually there's something super important about that. And the easiest way to test this would be to simply fill in a hex 90 into the command field instead of a 9, which is what I did. And I don't know if useless is still here, but that's exactly why the 90 was commented out here, is because I was just trying to replicate what their print statement looked like. So we can try it. I don't think it worked, but we can try just for fun. Okay. So now this time, this is the second time. The difference is that instead of, the 9 being directly after the previous 3 bytes, we have a hex 90 there. And this thing is still empty. Ugh. What's up, PackVane? Definitely do a clean desk policy. I try. It's just for streams. I clean it up, and then when the stream's done, I put the huge mess back on it. No, just kidding. All right, I think it's about time we all took a quick 20 seconds to take a break. I'm gonna get some water. I'll be right back.
This is a certified hood classic.
Okay, that was cool. So let's just record what we tried. Initialize the script with DD, didn't work. use hex 90 like the MIT course reference, even though I think it's wrong, didn't work. One more idea I have. Okay, so we could really fully copy the MIT course code. Look at another OS and copy it. That's something we could do. That's even not the MIT one. We can also use a virtual adder instead of a physical one with a lot of question marks. And the reason I have this is because so the MIT course used a v-adder, I think, even though the manual says to use a p-adder. So that's sort of weird, but that's also pretty easy to try while we're running out of ideas. So just for, yeah, I mean, we can kind of see how this buffer adder thing is used. PCI DMA read. Read from an address space from PCI device. Return a memtx result indicating whether the operation succeeded or failed. You know, the interesting thing is that that return value is not used in the qemu code, but might be interesting for me to just print out to see what happened with it. Stupid question, p-adder is virtual address and p-adder is physical address? Yes, exactly. Also not a stupid question, but yes, that's right. Because I'm wondering if there's something messed up with just like how the NIC is accessing memory, actually. And I'm a little bit curious. So this would be pretty easy, I think. I'm just gonna do get the red val here and print it out as a 32-bit unsigned int. I'm still trying to see how useful Copilot is. I mean, that would not have been too hard to do on my own, but so this, right. Let's give it a shot. I don't know. It's kind of fun to build qemu though, so I'll just take any opportunity I have to use my qemu. All right, why is this window looking kind of weird? Okay. Holy crap, whoa, wait a sec. Hello, dump, receive, IOV, capturing 110 bytes. That means, wait, whoa, 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 whoa. I'm capturing that in 4K, whoa. Why did that log message appear? Was that always, that was not always there, was it? Yo, what? The PCAP has data now. So did the 90 thing work? No way. Wait, whoa, whoa, whoa. Back up 1 second. Did that actually work? Wait, running this one more time with the 90. Maybe I should have been a bit more tempted. Why? Okay. iTerm 2 has now added this like weird UI thing. All right, we are moving qemu.pcap. Okay, so I wasn't going insane. There's nothing there yet. It looks like it didn't work. However, it like weirdly appeared later, right? If I exit qemu, it doesn't appear. Okay, that's crazy. My theory is that some kind of timeout happened, which caused qemu to flush the packet data or something weird. Wow. So something was happening. So yeah, it really, it actually kind of is working. But actually, yeah, and it seems it worked with the hex 90, which is what I thought was wrong, but maybe I really am like misreading this somehow and making a very like stupid mistake. But I could have sworn that the 9 should have been in like the low nibble. It's totally crazy that you can use Copilot directly in the code base to write code for you. Yeah, that's cool. So that's okay. I don't know why my iterm2 looks so weird. Okay, well actually, now we get this PCI DMA read thing, which returns 0. And that means memtx okay. Which is just confirming that okay, yeah, so here's where it reads the descriptor, and then it like prints some stuff out about the descriptor it received. Then it processes the descriptor. So that was quite alarming, but it actually did work. So now the question is how to make it happen again. Dump receive IOV, right? And this is with the weird hex 90, which I still don't understand. Is there anything I did to provoke that? I don't think so. So we could go back into the qemu code and actually look at this dump thing, and we could look for the caller. The only caller is this filter dump receive IOV. You can see where that's called, and that's some like callback thing. So it creates this object. not super helpful. What application for this packed source control console, etc. This is iterm2. This is just like terminal with tmux with a bunch of panes, lazy git in the top right for git. Yeah, that's pretty much it. Yeah. Maybe if I do something weird, like disabling the nick or something like that, I can cause qemu to like flush itself. Something like that. Capturing 110 bytes. 110 bytes is kind of a strange number, because that is not the backing buffer size. Each backing buffer is 128 bytes. Okay, I'm gonna get rid of some of these obnoxious hex dumps. Like this. Oh wait, okay, there it is. Okay, so if we wait long enough, some kind of timeout happens. And it actually, like, purges the data. Let's take a look. So, like, yeah, this is actually garbage data, I think, because I'm sort of stupidly just like transmitting an uninitialized buffer. So, but I think we can somewhat reproduce this now. So I'm just going to do something simpler, which is 16, right? And we'll just transmit some of these and see. It's like kind of obnoxious that there's like this random timer, it seems. Like a minute or several minutes or something like this. So while that's sitting there, we can try to move forward by reading more about qemu. In particular, we might try to find the caller of this receive IOV thing. And I'm going to guess it's called like this. Qemu deliver packet IOV. And that's where it happens. So it's this like qemu deliver packet function. Kind of separately, there is this, I don't know, net filter thing. But it's one of these. These are the only call sites. Qemu deliver packet IOV. So we just kind of walk it. And I even have IntelliSense. That's cool. The header. So this is like the only caller. Ah, okay. And that's a function pointer that gets passed somewhere else. And this still hasn't gone off yet. I don't think there's anything I'm doing that could help. Like, from qemu's perspective, the CPU, like the kernel is like just kind of sitting here. So I don't think like interacting with it really helps. I think it's just this strange timer looking thing. Maybe we can search for that. Qemu net filter dump timer. Once you've shut down qemu, you can examine the dump dat file. So maybe it's something very simple, like you need to shut down qemu in some kind of graceful way, which I'm not doing. It still has not happened yet, so maybe that's the question. Qemu, how to shut down gracefully on CLI. So usually I use this X thing to exit qemu. Maybe I'll try the qemu monitor. Qemu monitor. Help. Drive add, dump. Okay, so what if I do quit? It didn't write it out. Super weird. So all we know is that just like sometimes it actually does work Maybe the problem is with this panic or something. What does panic do again? Panic. Okay, there's only one. Why? All right, 20 seconds. Be right back. Here's the panic I'm looking for. It does. Maybe it's the panicking, which, I don't know, clears interrupts or something. But then just like spins. But maybe, it's like very odd, but maybe actually it was actually important to transmit a very large buffer. So maybe rather than this, I'll just do x44 or something. What if I just do this a lot? Will that? I don't know. Maybe that is a very simple thing to do. So I ostensibly just tried to transmit a bunch of data like through the NIC in hopes that it would fill some kind of buffer and cause that to like flush it to the PCAP. But that did not do it. All right. What else can I do? So it works like sometimes. What happens if I don't panic here? What actually is going to happen? It's going to hit this thing. That still didn't work. Then it like tried to like start user space and do a bunch of stuff. But I don't think that was a very good idea. This is basically the same thing, just panicking a little bit later. Okay. Maybe I can Google for this. Qemu filter dump net after timer? Empty. This is all exactly like I have it. So is there something I can do in my driver to like trigger it better? Alternatively, no, but wait a sec. It definitely worked. I'm like very sussed out by how this 90 is there. Showing 110 bytes. Which is a very weird size to capture. Well, we made a bit of progress. It's like kind of deep in the weeds to really understand the control flow of qemu here. There's this deliver packet function which does some stuff and then calls the net client state pointer which is registered here and is ultimately the thing that has our print in it. So we need to figure out how to trigger this. So maybe, what could I do? I could search for like a timer in the code here. So it's not really happening anymore. It happened twice. This is like kind of a stupid idea, but I'm just going to try 99, actually. Just put 9s in both places. And that did it. That worked. Hello, dump. Receive the, it's like, it's all there. Something is so strange about that, okay. So now we can look at our packet data and we can just observe a bunch of stuff being sent which has a 44 and then a bunch of zeros. And that is exactly what I am writing here. 44 and then zeros. Whoa. Okay, that was probably one of the stupidest ideas I think I've ever had. Just put 9s in both places because I'm not sure which one's right, but did that seem to work?
This is a certified hood classic.
Yeah, all right. That actually seemed to work and is reliably transmitting data from like via the NIC. I'm gonna call that a huge checkpoint. Okay. Wow. We are at what? 135 in the stream. All right. I'm gonna make a note of that. Or put it here. Okay, that was wild. But now the fun part begins. So what happens if I do a regular 9? That actually is also working every single time. So what is going on? What happens if I put zeros? That is not working. What happens if I put 9t? That is also not working. But so maybe there's something just stupid with that line that I am not seeing at the moment. But we can reliably write the data. Wow. I'm just curious, what does TCV dump look like? Yeah, that's kind of cool. Whew, I think that's time for a git commit. Yo, what's up, Phantom Deluxe? Yeah, unfortunately not. I would not really say this is beginner friendly. It's a bit more advanced. So now what I'm interested in is it actually important to send all this data, or does a simple 16 bytes? Yes, it does work, capturing 16 bytes. And we got our nice 8. Okay, perfect. So I can get rid of all of this too. Maybe I'll just leave in 1 just for posterity. And it's kind of interesting that actually when I do this, this is interpreted as two separate somethings. I don't know if it's like Ethernet frames or packets or something, but it is logically broken up, which is very interesting. So it seems like each descriptor send triggers a discrete data transmission from at least this PCAP's point of view. Okay. So that's kind of cool, actually. So now I'm just super confused. Maybe it was the stupidest thing ever, but is this not right? Now it's working. I am completely baffled. Or just this. Is it just completely reliably deciding to work every single time now? Because it really seems like it. What happened? I haven't changed like anything important in qemu. And did I change anything on my side? Not really. Okay. Hey, what's up, Hawkman? When I'm done with Lab 6, would I consider doing labs in other MIT courses? So the thing is, I've actually done all of the previous labs. You can check out my previous streams. I started at lab 1 with like this like course work right now. So I've actually done all of the labs. I think what's important for me is just to make sure I'm not actively doing the labs for a class that is running in real life right now with real students that are taking it. Because I think that would be disrespectful for like the tutors and like the course teachers and professors that are making this available. I would maybe consider it for other older courses that are not actively running, but actually I'm not super motivated to do that because I've gotten a lot of what I came for by doing these courses already, and I'm feeling a bit more ready to kind of go out on my own into the OS world. Wait, so actually, yeah, wait, no. Here is this thing. Maybe that was important. Also, why no week in the title? I'll add it to the recording. Like I usually add the week number after the stream ends for the record, but I don't put it in the title as I like actually stream. I think that like reduced. It was just the theory that it reduced people like clicking or something. Wait, so what happens if I comment this out? That might actually be the important part. No, it still works. What the fuck? Oh my god, I literally don't know what happened. I don't know why it's working every single time now. Like nothing substantial actually like really changed. That is so frustrating. It's like you can tell it's working because of this hello don't perceive IOV capturing 128 bytes. We're seeing that every single time. Yeah, this is the last lab. Well, technically, is there lab 7? I do not think there's a lab 7. So here's the thing. Lab 7 is like the final project, and people taking the course have the choice to simply do lab 6 for their final project, which is what I'm doing. It's like the default project. Or you could go out on your own and think of your own final project. And I decided to not do that. So as far as I'm concerned, yeah, it's pretty much the final lab for me, unless there's a secret lab 8, which is, no. Yeah. Yeah, it could be possible that Mark OS would actually begin somewhat soon. Although I still need to get through the rest of this lab, which so far has been like super hard. But yeah. So I'm just going to stage all of this. So the forbidden lab. Exactly, yeah. It's that. Do I think the labs are difficult considering these are done by students in the age of range 18 to 24? I think the labs are of medium to high difficulty. This is by far the hardest one I've done. Actually, for the earlier ones, I was kind of surprised and also very grateful that a lot of them were a lot easier than I was expecting. Where they provided you like with a lot of code and you just needed to fill in like a couple key critical parts. So I was actually a bit surprised at how easy some of them were, but also very grateful. I still learned a lot, but I don't know if I would have been able to like do this for so long if it was like really, really out of my league for like a very long time. Regarding the age, I don't know. This is like an MIT graduate course actually, so it's not really. I think there's probably some undergraduates that did take this course, but I don't think they were 18 years old. All right, quick 20 seconds. Don't forget to stand up and stretch, get some water. Yeah, so it's like a graduate level course, which means people are a bit older, but also like, I don't know, MIT students are pretty smart. Also, they are getting a lot of support when doing these labs, I would guess. Like they have TAs and office hours, and they can work in groups and stuff. So I'm finding it a bit more difficult because I'm like, I don't have any of that. So if we go to the website, class overview, yeah. Okay, maybe I'm wrong. It's intended primarily, for seniors and master's students who want to learn OS in detail. PhD students are welcome. Blah, 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 blah. Okay, I was wrong. Seniors and masters. I think they have like a different course. Oh, interesting. Related classes from other universities. I think they have a different course that's like a bit more undergraduate, slightly. Yeah. Okay. Do I think Lab 6 is harder than Lab 4? I don't remember what Lab 4 is, but this has definitely been the hardest lab of them all. What? Lab 4? I guess, yeah, no, true. Lab 4 was multi-core support. That was pretty difficult. I do have to admit that was pretty difficult. And that did take me kind of a long time, but still, no, I would definitely say this one is harder just because it's like, there's so much stuff with qemu involved, and the processor manual is so huge. So, Hui Hun, how do you start self-learning these kinds of things? Where do you start? Yeah, my recommendation is always Pone College for most people, which is like the highest quality learning resource, free learning resource for systems programming that I've ever seen. I also have like a couple random links on my blog, which you could try. Am I running with the data cache on? I don't know. You would know better than me, about that probably. As far as I know, I've not done anything to disable it. The only qemu options are listed here to add the disk, I don't know, configure the number of cores, file system disk, and the networking stuff. So, well, that sounds like a world of pain. Data cache, non-determinism. Something you have enabled from inside your OS. Yeah, I don't know. I'm not doing a very sophisticated approach, and I'm also not really using any barriers or anything like that. So it could be possible that there are weird memory related things, but it's actually not that non-deterministic. Like now it's like working every single time. Which I still don't understand. Yeah. Nah, it's like non-deterministic in the sense that it wasn't working, and then now it suddenly is just like always working. But now it just seems to be completely stable. Actually, wait a sec. No, I removed the panic here. I wonder if that was, I would be so annoyed if that was the reason. Yeah, now it's not working. But if I panic, oh shit, no. Okay, so it was actually the panic. That is so annoying. But very interesting. So I originally just had this panic in the code because I didn't want the kernel just like start executing a bunch of random stuff. I wanted to keep it pretty tight and controlled as far as what code was being executed. But it seems like that actually interferes with qemu in like some sort of timing way, panicking too early, and breaks everything. That is very interesting. It's always these like really stupid things. All right, catching up with the chat. Pac-Man, multi-core support as in multi-threading. Actually, no. You can have multi-threading even just on a single CPU core where threads just like share the CPU and get scheduled out. But Lab 4 was really enabling multi-core support where you actually enable all of the processor's cores that are available. You can run multiple threads on those cores, but they're different concepts. And yeah, multi-core support allows you to like achieve actual hardware parallelism as opposed to kind of just multitasking on a single core. Why don't we use Vim rather than VS Code with Vim? VS Code is just too good. Yeah, just too user-friendly. And I also use it at work, so I'm just used to it. All right. Well, that was cool. I think I'm actually going to leave it here today, guys. I'm not going to try to start something new in the remaining time, but we can, I think we can consider exercise 6 finished. That was annoying, but it just, so, and I think actually this thing is wrong. I literally think the outcome of the investigation is that this should not be a 90, it should be a 9. Because the documentation says so, and I think, and like, it just doesn't work if you use 90. Am I right? That did not work. And this did. So yeah, like I think it was just like a weird copy and paste issue they had or something. But I think we can consider exercise 6 accomplished.
This is a certified hood classic.
And we can continue with whatever's next week. Also, feel free to join my Discord and whatever, and we can chat more. All right, y'all. Hoping you have a great week. Have fun hacking on whatever you're doing, and I'll see you next one. Later. Thanks for all the help, John. Appreciate that. Bye, guys.